Hi, everyone. My name is Max Rizzo, and I'm a graduating senior here at the University of Arizona, graduating with physics and astronomy. And I did my research, my senior thesis, under the NASA Arizona Space Grant. So I was one of the Space Grant students, and I'm very supportive of the Space Grant and all the opportunity it gives. So if you're in the audience and you're likely a eligible mentor, I would really suggest you apply. I mean, you're already doing the research. It's basically free money. So I would really suggest it. So for my project, I basically revisited the entirety of the FUSE data archive. It's another acronym, I know. I'm just going to click through these. So the FUSE telescope it stands for Far Ultraviolet Spectroscopic Explorer, and it will be on the next slide. But basically, the entire goal of the FUSE was to make UV emissions, or UV observations on different types of transient objects outside and inside the Milky Way. So UV detection and observation is really hard to do. Classically, you have to go to the atmosphere. It can't be done from the ground. The atmosphere does a really good job at shielding and protecting us from all sorts of UV rays. It's okay. That's good. We got to share with the Zoom. Sorry about that. That's good. So Carlos walked through this exact diagram, but the CGM is incredibly important to galaxy evolution, and not only galaxy evolution in the present, but how galaxy evolution changes over time or with redshift. So the CGM, as he described, it's the reservoir for star-forming fuel. Stars are exploding and accreting winds off due to supernovae and other types of massive stellar winds. Black holes and other types of massive objects are accreting gas. Gas is constantly being ejected, recycled, cooling, and then falling back down to the disk. Some stars in the disk will shoot hot jets of warm, hot gas. The gas will then be above or below the disk, not in presence of any stars, will be able to expand and cool, and then later fall onto the disk as gas wind. So the dynamics here are very complicated. The temperature ranges from 100 Kelvin to 10 to the 6 to 10 to the 7 Kelvin. So the dynamics are extremely rich, and it's very hard to characterize what is actually going on with the CGM. Additionally, making actual observations of it is next to impossible. You can do it inside the Milky Way, but outside the Milky Way, it's extremely difficult to make these types of emission. Inherently, because the type of gas that is doing the emission is O6 gas, and it is CGM, so it's inherently diffuse and it's non-stellar. When most of us think of galaxies, we see galaxies as clumps of stars, right? We think that it's intuitive to think that the majority of baryonic matter would actually lie within stars within a galaxy. But as some of you in the audience might know, when stars form, actually, it takes so much gas to form a star that there's more gas outside of the star than there is inside the star itself due to the gas required to release the gravitational pressure for collapse. So this means that within the majority of galaxies, 80 to 90% of baryonic matter is not in stars. In fact, it's in this CGM. It's incredibly dynamic and difficult to observe, but it's also incredibly important because it's literally the dominant source of matter for galactic evolution and star-forming regions. So our best chance at making any sort of observation on the CGM has been historically the O6 line emission, which stands for 6 times ionized oxygen. So it's damn hot. And so this really is characteristic of the warm, hot gas, which is a name we give to gas around the temperature of 10 to the 6 to 10 to the 7 Kelvin. So this next plot is various emission lines of the CGM. On the y-axis, we have temperature, and on the x-axis, we have density, or column density. So really, we're looking for something that maximizes both of these parameters. So something along the y equals x line would be most optimal for making O6 observations, because it would be both very hot in terms of brightness, but also very dense. We need a significant surface brightness in order to have any sizable emission at all. So that brings us to FUSE, which is what this project did most of all the work on. Basically, I revisited the entirety of the FUSE observation catalog. It was a very successful far UV spectroscope that was launched in 1999 and observed till 2007. Its functional range is from 90 to 120 nanometers, so it's about that Lyman alpha UV. But it has, so it had 4 different overall apertures, and 2 of them were optimal for O6 signal. It actually had 2 MCP detectors in it, and it had 4 different, within the 4 different channels, each one was had very carefully optical coatings in order to give maximal performance for that channel. So this wavelength range covers a lot of useful information, as I said, and it really is the dominant component or indicator of warm-hot gas. So overall, throughout these 8 years, FUSE produced 5,000 total exposures, around 6 to 8 hours each. On each object, it tried to do 2 observations or exposures, one during the day and one during the night, in order to offset that systematic error that's present from the sun. So there's about, give or take, 2,500 objects observed by FUSE. Yeah, a picture on the right also shows the size of the FUSE telescope. That's actually a person in the little window on the right. So the Aspera mission, which is going to be launching in 2024, which is like the size of a shoebox, is a lot smaller than the FUSE spectroscope, which is 20 feet tall. So basically, I have to, the process for this searching through the FUSE catalog is, it's a combined manual and automatic routine. So I loop through and I obtain a visual band image using the DSS archive. And then basically I take my image and I overlay FUSE pointings. So what you're seeing on the right is visual images of NGC 4631 and 891, which are the 2 only known detections of O6 emission signal. And on top of it, you can see there's boxes. So the box is the low resolution FUSE aperture. The red slit is the MWRS, the medium resolution, and then the cyan slit is the highest resolution slit. The red and cyan slits actually weren't used by FUSE because they were too high resolution that they left the pointing so little margin of error that FUSE could not accomplish the targeted pointing requirements in order to use the middle and high resolution slits for any types of science. So this study strictly used the LWRS, or the low resolution box slit. So basically I would loop through every single object, every 2,500 or 5,000 exposures. I would make a plot like this, and this plot tells me a few things. It tells me the relative location of the galaxy. If they all have the same scale, so if they're like a point source, that indicates that it's very far. Things with structure, spiral arms, usually that indicates that the galaxy lies a lot closer and it's actually of interest. So this allows me to trim out the total number of objects. Objects that lie really far away, I can just 96 them because they're point sources and there's no chance that any sort of O6 emission would have been detected. Detecting any sort of emission has to be done on the disk because, as I discussed, it's not stellar. So if we just point our spectrograph at a galaxy, we're just going to get swamped by stars. So you have to point the spectrograph slightly above or below the disk, which makes it very hard for distant objects, almost impossible. So that's why distant objects were thrown out. So this allows us to begin trimming the amount of observations. Here's some more plots. So class 85, it says 54, but it should say 85. In the middle is actually examples of some bad targets. So those are all really far away, and you could see they all just look like point sources. So I didn't consider quasars at all. They didn't have any opportunity to contain the O6 signal. Spiral galaxies and starburst galaxies were both very useful and principal components used in the analysis. Here's some more plots. Some on the left are elliptical galaxies, and then on the right are some of the most objects that were of very high interest. In the bottom right, there's 4631 and 891, which again are the only 2 known detections of O6 signal. The rest are just candidates. And basically for each of these pointings, the CalFuse data reduction pipeline is completed. Basically what it does is it produces a background reduced spectra, given you input the spectrum, the two raw spectrum files, and it does advanced analysis in order to compute a mean background level, subtract off the background, and do a very precise histogramming and binning into a nice spectra. So this is what the spectra look like on the right. You could see even for 891 and 4631, which are the only things plotted, it's very hard to tell if there is any signal at all. So the signal is about at 1032 angstroms. It's within the shaded region. And so if you look at the top left and top right, you could see it looks like there is some O6 signal right there in the middle, pretty definitively. Even then, it's only about a signal of noise to 5. But for some of the other detections, like right here, 4631-I, there's the signal to noise. It's still actually 4, but some of the other ones, we didn't even fit a signal to noise because the O6 emission just wasn't even present. And throughout all these exposures, even the one where we actually have a positive O6 detection, you could see that the photons are in the amount of 30 to 40 photons for an 8-hour long observation. So we're counting single photons, and we need to be sensitive to single photons. And the total integrated signal may just be less than 100 photons for that total integrated signal. So it needs to be very sensitive. And the CalFuse was a data pipeline that was designed in order to create this very sensitive data reduction. So we defined a hit to 3 alpha confidence, or a signal to noise ratio of 3. And we looped through every observation ID in order, while discarding the ones that are too far. And it's still in process. I have all the data downloaded on my computer at home because I realized downloading it every time I had to run the code was not efficient. So I just downloaded it once. I bit the bullet, and I have all the data on my computer at home. But I'm still trying to loop through and to increase our number of O6 detections. I do plan to verify the NGC 891 and 4631 as the only 2 known extragalactic O6 emission known sources. And I plan to increase that target list to maybe 4 to 6 objects and set minimum levels on other targets. So this was completely in support of the Aspera mission, which Carlos gave a great job talking about, and an update with the review coming up in the next month. But it is going to basically repeat entirely what Fuse did in CubeSat form. So it's trying to accomplish the same scientific goals as Fuse, but with a cheaper budget and quicker deadlines, and with a much smaller form factor. Additionally, it's going to achieve, or it's spec to achieve, sensitivities twice that of Fuse. So it's likely that it's going to drastically increase the amount of O6 detections, and it's going to have more exposures than 5,000. Overall, this is going to be really important, and it's going to significantly constrain our CGM, our knowledge of CGM behavior and evolution. Right now, for galaxy evolution, we really our theoretical models really rely on what we can observe from stars, and we really lack any sort of observational evidence or knowledge about what is actually happening to the CGM, about how much gas is in what phase and how much gas will accrete to a star versus different stages in their redshift. So in order to actually go from guesses or free parameters to things we have constraints on, the Aspera mission seeks to increase the amount of O6 line emission signal detections. So I'd like to thank my advisor, Han Chung, and the support of the University of Arizona Space Grant Consortium and the Astronomy and Physics Department. Questions?
Thank you for your talk. I have a question on the slide page 264. You have used the spectrum,
264.
a nice spectrum, but
could you speak up? Sorry.
On this spectrum, this spectrum that you you have used the spectrometer, that is calibrated or not?
I'm sorry, could you repeat the question?
The spectrum that you have
Yeah.
shown here, that is taken from a spectrometer, and that spectrometer is calibrated in different sections or different regions?
Yeah, so the fuse does do background subtracted, and it will produce background subtracted spectrum for the different objects, and the background levels could change in time because it doesn't necessarily expose one object after another. It might move to a different field and then come back. So I think these observations likely were separated by a few days in time. So yeah, they had to be calibrated with their corresponding background levels at the moment in time that they were observed.
Because some of the peaks are saturated in different regions.
Yeah, so I didn't mention it, but the peaks that are saturated are actually artifacts from Earth. So the ones that have like a little circle with a line through it. So the saturated peaks are just artifacts that we expect from different types of molecular emission or elements in the atmosphere of Earth. So
Thank you. Thank you.
Thank you for the nice presentation, and it was very good. I learned a lot. So being much smaller than fuse, Aspera is much smaller, but also 2-channel versus 4. You say it will have twice the sensitivity of O6 detection. Could you tell me how that is possible using Aspera versus fuse?
So Aspera also has actually a very low effective throughput given this size of the apertures and the effectivity of the optical coatings, but I think it's a big improvement from Fuse. Fuse was built in 1999, so we've had 20 years of developments with optical coatings and MCP detectors. And yeah, so I think it's really just the development and microchannel plate detectors, which is not my expertise, and developments in optical coatings that we can achieve the twice the sensitivity with, I think, even maybe a smaller aperture effectively. So, yeah.
Thank you.